Hey everyone, welcome back to The Explainer. I'm absolutely thrilled to have you here today because we're taking some incredibly complex mechanics and breaking them down so they're brilliantly simple. Okay, let's dive into this because today we're tackling something that honestly feels like absolute magic every single time you head to the airport. We are looking at the anatomy of flight. I mean, think about it for a second. How exactly does a 100-ton machine just stay up there in the sky? It's this massive mechanical and physical puzzle. We totally take for granted how easily a commercial airliner, weighing over 500,000 pounds, just effortlessly lifts off the runway. But there is this incredible symphony of physics, engineering, and fluid dynamics happening right outside your window. And today, we're going to solve that puzzle together. To really appreciate where aviation is today, you have to consider this unbelievably rapid evolution. Back in 1903, Orville and Wilbur Wright managed a 12-second flight. 12 seconds! And that was in a wooden frame with a tiny 12-horsepower engine. But then, just 36 years later, in 1939, Germany tested the Henkel He 178. That was the very first aircraft to fly using a jet engine. I mean, wow. That is a rapid, mind-blowing leap from a quick little hop on a beach to the foundation of modern jet propulsion. So here is our flight plan for this explainer. We're going to break this massive machine down into 4 logical, digestible building blocks. First up, the 4 forces of flight. Second, the truth about lift. Third, how jet engines work. And finally, steering in the sky. All right, let's kick things off with part 1, the battle of forces. Anytime an aircraft is up in the sky, it is caught in this invisible, continuous tug of war. And this epic battle plays out across 2 different axes. On the vertical front, you have weight constantly pulling the plane down toward the center of the Earth, while lift is the aerodynamic force actively pushing it back up. Then, over on the horizontal front, drag is basically the air resisting the motion of the aircraft, pulling it backward, while thrust from the engines propels it forward. The absolutely crucial point here is that for an airplane to just cruise nicely at a constant speed, all 4 of these forces have to be in perfect balance. Which brings us nicely to part 2, the truth about lift. We all know that the weight of an airplane is massive, right? So how on earth do the wings actually generate enough upward force to overcome it? Well, Professor Holger Babinski over at the University of Cambridge points out this really fascinating misconception. He says, I start by giving the wrong explanation, and only a handful will know that it is wrong. What he's talking about here is a total myth that has been taught in textbooks and pilot manuals for decades. It's called the equal transit time theory. Basically, it's the idea that air traveling over the curved top of a wing has to speed up just to meet up with the air on the flat bottom at the exact same time. Turns out, yeah, that's completely false. So what's the actual truth? Well, it's all about curvature, not distance. When you introduce a curved shape into the airflow, like an airplane wing, which is officially called an airfoil, it actually curves the streamlines of the air. This creates a pocket of lower pressure on the top surface and higher pressure on the bottom surface. And it's that higher pressure down below that literally pushes the wing upward. It's actually the exact same reason a thin sail on a boat generates force. When it's rigged, it curves, acting just like an airfoil. Now, believe it or not, there's actually been this huge, heated debate in the physics community for years. People argue over whether lift is caused by Bernoulli's principle, the pressure differences we just talked about, or Sir Isaac Newton's third law of action and reaction. Well, NASA officially states that both are absolutely correct. Bernoulli's equations explain the pressure changes in the gas velocity, while Newton's third law explains that as the wing redirects or turns the airflow downward, the air reacts by pushing the wing upward. They're basically just 2 different mathematical ways of describing the exact same beautiful reality of flight. But here's the catch. Lift requires motion. No motion, no lift. It's that simple. But different aircraft achieve this required motion in entirely different ways. Fixed-wing aircraft have to physically barrel forward down a long runway to force enough air over their wings. But rotary-wing aircraft, like helicopters, they completely cheat this rule. Their wings are the rotor blades. By spinning those blades really fast around a shaft, they're moving the air over the wings without the actual body of the aircraft having to move forward at all. That is exactly why helicopters can just hover in place and take off vertically. All right, moving on to part 3. How jet engines work. Now, what's really interesting to understand here is the engine's true job. 200,000 pounds of thrust. Think about that for a second. Here is a seriously mind-bending fact for you. A modern airliner might weigh over 1 million pounds, but its 4 engines combined might only produce 200,000 pounds of thrust. Why so little compared to the weight? Because the engines do not lift the airplane, the wings do the lifting. The engine's only job is to overcome drag and push the plane forward fast enough so the wings can do their magic. So how exactly do these incredible engines generate that forward thrust? It is a brilliant 5-step process. First up, a massive fan sucks in huge quantities of air. Second, the compressor, which is this crazy series of spinning blades, squeezes all that air into a highly pressurized, tiny space. Third, we hit the combustor. Fuel is sprayed right into this squashed air and ignited, creating a literal 2,700-degree fireball. Fourth, these rapidly expanding superhot gases blast backward through a turbine, spinning it thousands of times a minute, which, by the way, is what powers the compressor at the front. And finally, the air shoots out the nozzle at the back. As that hot gas blasts backward, the engine and the whole plane are thrust forward. Over the years, engineers have adapted this core process into a few distinct types of jet engines. You've got your early jets, the turbojets, which were super loud and really fuel-hungry. Then there are turboprops, which use the jet to turn a propeller, great for slower, regional flights. But modern commercial airliners, they use turbofans. In a turbofan, a huge chunk of the air sucked in by that big front fan actually bypasses the fiery core entirely. This cooler, bypass air wraps right around the hot exhaust, which drastically reduces engine noise and seriously increases fuel efficiency. It's genius. Okay, so now we have our thrust and our lift, and we are airborne. But how on earth do you maneuver a 100-ton object through 3-dimensional space? Let's check out part 4, steering in the sky. And this brilliantly illustrates exactly how pilots pull this off. They use specific flight control surfaces to move along 3 different axes. The ailerons, which are out on the outer edges of the wings, control the roll, so tilting the wings left or right. The elevators on the horizontal tail control the pitch, pointing the nose up or down. And the rudder on the vertical tail controls yaw, swinging the nose left or right. Now, here's a super crucial point about flying that is totally different from driving a car or steering a boat. You don't just use the rudder to turn left or right. Turning an aircraft actually requires a banked roll. When the pilot uses those ailerons to bank the wings, that massive upward lift force is suddenly tilted at an angle. And it's actually the horizontal component of that tilted lift force that grabs the airplane and pulls it through the turn. There are also some secondary controls you have absolutely seen if you've ever had a window seat. Flaps and slats extend out from the wings during takeoff and landing. They physically change the shape and the curvature of the wing to generate extra lift when the plane is moving at slower speeds. And when you finally touch down, you'll see those panels on top of the wings suddenly flip up. Those are spoilers, and their job is to intentionally disrupt the airflow. They basically dump the lift so the plane's weight settles firmly onto the wheels for braking. Now, since we're talking about moving through the air, we have to mention turbulence. Look, when the plane starts shaking, it's really easy to get nervous. But turbulence is simply an irregularity in the atmospheric airflow. Think of the atmosphere as a giant ocean of moving air. When the plane's wings hit uneven air currents, or air pockets, you get a bumpy ride. It is perfectly natural, and the aircraft is heavily engineered to handle these mechanical stresses with total ease. To wrap up our explainer today, let's take a second to reflect on this symphony of flight. We've seen how the engine's thrust fiercely conquers drag, how the clever curvature of the wings manipulates air pressure to literally defeat gravity, and how these hinged surfaces on the tail and wings give humans total mastery over 3-dimensional space. It is a perfect, physics-driven symphony. So I want to leave you with this question to ponder. Next time you fly, which force will you notice first out the window? Will you be watching the flaps extend to increase lift? Or maybe you'll be listening for the turbofan engine spinning up its thrust. I really hope this explainer has transformed the way you view air travel, turning just a regular plane ride into a front row seat to the wonders of physics. Thanks so much for learning with me today, and I'll catch you in the next one.